Okay, we left here talking about the sigma algebra generated by a random variable, the sigma algebra generated by a collection of random variables, and the definition of a monotone class of functions, which is basically a set of functions which is closed by linear combinations and increasing limits. With this, we can state the monotone class theorem for functions. Opa. Let M be a monotone class of functions on E. Suppose that the indicator of A is in the class for any A in the sigma algebra in a collection C, where C is a p-system that generates E. Okay, so suppose that the indicator of A is in the collection M for any A in the collection C, where the collection C generates the sigma algebra E. Then MB includes all positive immeasurable functions and bounded, all positive and bounded. Okay, so this is the statement. So consider, I don't know why I wrote, no, it's just simply M without B. Okay, let M be a monotone class of functions on a set if it contains the indicators of all events in a p-system that generates the sigma algebra. Then it includes all the positive and bounded functions which are measurable with respect to that sigma algebra. Well, let me write it again for practice. Let M monotone class of functions on E if the indicators of all events are in M for all A in E, then no, for all A in C where sigma algebra generated by C makes E, then M contains all positive and measurable how can we put it? Then all positive and measurable functions with respect to E are in M. Maybe this notation is not very good, but this is the idea. So let's read here. This theorem is useful because if you have a monotone class of functions on E, then you can check that this class contains the indicator function sets that are in a p-system. This is a bit confusing. This theorem is useful because if you have a monotone class of functions on E, then you check that this class contains the indicators of sets that are in a p-system, and then the theorem tells you that M includes all positive and bounded immeasurable functions, which is basically what we said. And we will use this theorem to this theorem to prove the next one, which is concerned about the representation of random variables measurable with respect to a sigma algebra generated by another random variable. Okay, here it's called theorem delta. Let x be a random variable taking values in the space E. Then a mapping V from omega, right, yes, to R extended is measurable with respect to E if and only if it can be written, let me see, to the sigma algebra generated by X. This should be this, if and only if V can be written as a deterministic function applied to X. So this for any f which is measurable with respect to E. So basically any function of a random variable is measurable with respect to the sigma algebra generated by that random variable. Proof. Sufficiency. Let's put it like this. Oh, okay. So consider a collection M of all V of the form f applied to X for f in E. What we have to prove is that this belongs to the sigma algebra generated by X. Here it says so what we want to prove, that M is contained in the sigma algebra generated by X. Now, considering that measurable functions of measurable functions are measurable, and that f is in E, we can say that X belongs to sigma algebra generated by itself, well, and since this thing, then V is measurable with respect, V is sigma X measurable, which means M, the collection M, contains the sigma algebra generated by X. For the necessity part, So here we start here for this direction, for the sufficiency, and we basically use the fact that measurable functions are measurable. And okay. Now necessity. We want to prove that the sigma algebra generated by X contains all things of this form. No, here it says that it contains, well, it's the same thing, because M is this. M is the set of these things here, basically. And to do this, we first have to prove that M is a monotone class of functions. And to do this, the indicator of phi belongs to M for any E. Well, because the indicator of the entire set, okay. The indicator of the entire set belongs to this because it can be written as f applied to X, where f is 1, is the constant function for any X. f of X is 1 for any X in E. Let U and V be in the monotone class, random variables in the monotone class, and A and B real numbers. What we have is that AU plus, well, we have to show this. Then U, which is F applied to X, V, which is G applied to X, or Y, X, for F and G measurable. We construct AU plus VB plus BV as A F applied to X plus B G applied to X where H I don't really understand this point very well, but now given Fn or Xn, okay, how is it called here? Here it says, since we are able to express the linear combination of these in this form, we can say that AU plus BV is in them. Well, And now we have to consider a sequence. Consider Vn in M. What we have to show is that if it increases to a limit V, the limit V is included in M. So for any n, there exists a function fn in E such that Vn is fn applied to x. And consider f to be the supremum of what? Of fn, which is in E. Then V, which is the supremum of Vn, or the supremum of fn of x. This is the same ff of x. And from this we can conclude that V is in M. Okay, so we proved that M is a monotone class of functions. Now, how can we use this? Consider H in omega such that H is measurable with respect to sim algebra generated by X, which means H is the inverse image of some set A for some A in E. And consider the indicator of H to be the indicator of A applied to X. This thing is in M. Why? Because the indicator of A is immeasurable and deterministic. And here we are using something which we like f applied to x is measurable. So this is one of the previous results that we have seen and we are using also here. So we have proven that M contains all the indicators of events which are measurable with respect to sigma algebra generated by X. Contains all the indicators of sigma X, and apply the monotone class theorem for functions. We have that M contains all positive random variables that are sigma-ed. So M contains all the random variables x which are measurable with respect to sigma x. Let's call V Now I would like to extend this not only to positive functions but for arbitrary functions. Now, okay, so we have this for positive functions. And to extend this, we let V be in sigma x, so that V we decompose it into the positive and negative part, which are both in sigma x. And by the previous point, we have that V plus can be written as G applied to x, G composed with x, and V minus, well, x plus, no. And this H applied to x with H in E, well, H and G should be both in E. And then we have this part is not, I think there is a mistake here. But in any case, we have that f of x is g of x minus h of x when the minimum this is the minimum, I think. Between them is 1, no, 0, 0, 0, and 0 otherwise. Therefore V has the composition form and therefore belongs to M. This means sigma x belongs to M, which is what we wanted to prove. Okay, let's write it. So V has the composition form, so it belongs to M, and this means sigma x belongs to M. E punto. Period. Okay, so by means of this result, at the end of the day, we know that well, this gives us a condition to check the measurability of random variables with respect to a sigma algebra generated by another random variable. Okay, good. It was less complicated, I think, than I initially thought of. Anyway, a corollary of this, a consequence of this result is the following. For any natural number ending in star, so positive natural numbers, let xn in the space E, En a mapping V from omega to R extended is measurable with respect to the sigma algebra generated by the collection if and only if V is a function of all these random variables. For some deterministic f, which is measurable with respect to the products in algebra. So this is simply for when we have when the index set is discrete, we just have this version. And well, here it says that this can also be extended to uncountable collections. And now let's consider the definition of filtration. So let T be a subset of R. Ft sub sigma algebra of H for any T. We say that the collection F of all these filtrations is called a filtration. Well, the collection F of all these sigma algebras is called a filtration if Fs is contained in Ft for any s less than T let me see. It basically, a filtration is an increasing sequence or family of sigma algebras. So this is F1, F2, F3, and so on. So Fs is contained in Ft for s less than T. This is s, this is T. S is smaller and it is contained in the one. Yeah, so this definition is correct. And the filtration is the tool that we use to model information, the flow of information over time. So it's the collection of all events. So any sigma algebra composing the filtration is the knowledge that we have up to a given time. And as time evolves, we accumulate more and more knowledge about what happens, what doesn't happen. And so this is the motivation basically for this mathematical tool. Okay, and one very important example of filtration is the filtration generated by a process. So consider X to be this collection here, and define f of t to be the sigma algebra generated by the collection, right? Up to 10. Okay, here it's defined in this way. Ft to be sigma algebra generated by xs with s less than t. And that's in the index set. Then, but I think this should be also, what do we consider as less than t for Ft? Well, here it says that Ft, this collection, is called sigma algebra generated by the process xt. And now let's resume the idea of independence. And we will in particular focus on independence between different types of objects. In particular, independence of a finite collection of sigma algebras, so called H to be this collection here, Fn, with a phi in H for I from 1 to n. Then H is an independency if the expectation of some random variables v1, vn can factorize into a product of the expectations of the individual expectations. For any, so this is the important formula to remember. For any vi belonging to the sigma algebra fi, well, which is measurable with respect to fi. And a proposition related to this is that let f1 fn be sub-sigma algebras of H with n greater than 2. For any I less than n, let script ci be a p-system that generates fi. So then we have that this collection here of sigma algebras is independent. So it's an independency if and only if the probability of all events h1 intersected up to hn factorizes into the product of the probabilities of these events. For any hi in fi. No, for any hi in the collection ci union with omega. I don't know why. It's ci extended. So it is enlarged, putting the space inside. And here one remark is that the notion of independence between random variables taking values in measurable spaces is given in terms of the sigma algebras generated by them. So if the information related to random variables is independent, also random variables are independent, I think. And one important proposition is that every partition of an independency is an independency. How can I summarize this? Partition independency is an independency. partition of an independency is an independency. And we don't have the proof here, but it will be used for Kolmogorov-01 law. And another example here, if we have a random variable x1 in E1, x2 in E2, if you're concerned about the independency of the vector x1, x2, then you should look at the sigma algebra generated by x1 and the sigma algebra generated by x2. Okay, I think we can pause here. So we recalled these notions of independence. We saw the monotone classification theorem of functions, which allows us to consider random variables measurable with respect to sigma algebra generated by some other random variables. And well, next time we will get back to this probably, just as a review, and keep talking about independence. Okay.